Now we are going to study little about sheet metal forming, and after that we'll jump to the joining and welding. So what is sheet metal operation? Now we have our work in a sheet metal form. So now we have to change its shape according to our desired application, and that is called as sheet metal forming or sheet metal operation. Just a second. Okay. So, what is a sheet metal? These all things we have already seen in previous session, like a product whose thickness is less than 5 mm is called as sheet metal. So, why we are doing sheet metal forming? Because suppose you have seen your cars, so the bonnet of your car or door panel, these all are made of sheet metal only. Firstly, what they do, they get a sheet metal, and then they got a rolling sheet, and then what they do, they form it according to the application. They'll form it in the form of uh, a door or a door panel, like that. So most common material which are being used as a sheet metal is low carbon steel, or in aircrafts, aluminum sheet metal is highly used. There are so many parts of a aircraft that are being made of aluminum and titanium, and mostly sheet metal is having applications in automotive as a bodies, frames, and also in aircrafts. So that is why it is important. That is why this forming is a different topic in your syllabus, because it has a very high applications. This is a very applied field. So this is one kind of sheet metal operation, that is piercing and blanking. So we have seen what is piercing, punching, and blanking. So these are the shearing operations. Shearing means separating the metal from the workpiece. Okay. So in the blanking, that the piece that will punched out become a workpiece, and in piercing, that punch out is the scrap, and the remaining strip is the workpiece. So if you get confused between blanking and piercing, see, piercing and punching both are almost same. There is a only size difference. If the size is more, then it is punching. Size is less, then it is piercing. Uh, and if you get confused more often between piercing and blanking, so piercing, you can see when we do nose piercing or ear piercing, in that the rest of the metal is of the use. Whatever is punched out is a scrap. So like that, you can remember what is blanking and what is piercing. And piercing and punching, PP, both are same. Only the size is different. Then what is metal shearing? Metal shearing is the process that removes unwanted material from a sheet metal. So what is the principle? A punch will push a workpiece against a die. So there will be a punch, there will be a die. So we have to give the dimension to our punch and die according to the shape and dimension that we want for our workpiece. So what will happen? The punch will move and it will push the workpiece against the die. So there will be our desired dimension on our punch or and die. So the some localized shear stress will form, and when this shear stress will be greater than the shear strength of our sheet, the material will be removed. Okay, so this is the principle of sharing. So this all we have already seen. The force which is required to the for continuing the sharing operation, that is called your blanking force. So this is punching and piercing is there is a size difference only. If the
पंचिंग द स्क्रैप मतलब जो पीस जो बाहर निकलता है वो होता है अपना जो मेन जो चाहते हैं ऐसा होता है ना
blank देखो see in this diagram you can see this is blanking, this is piercing or punching. Blanking may whatever the scrap, whatever the punch that is coming out, that will be your workpiece. And in the piercing, whatever the left material will present, that will be your workpiece. Okay, in this is your workpiece. In this whole part will be your workpiece. The difference between piercing and punching is of size. If the size is like whatever the holes that your whatever the punch blank that you are making are bigger in size, then you called it as punching. Otherwise, you will call it as piercing. So, like P and P, piercing and punching, both are similar operations. That how you can remember.
Madam, is there any it's related to shape that if you want to punch circular, then it is known as piercing. Is this true?
Uh, I don't know. Let me see. Like I don't think that it is based on the shape. As much as I know, it is based on the size. If the size is more, it is called punching. I will check.
Okay. Ma'am,
Yes.
is the size to be important to remember?
No, it is not important to remember for your syllabus. Okay, so this is the diagram of shearing. Punching and blanking both are the shearing operation. Means you are separating the metal from the workpiece. So one blank will be there, one die. This is your die. So we have to provide some clearance between the punch and die. Can you tell me why? Because because yeah, there should be some gap between the die and punch.
The shear area happens, the metal expands.
Yes, and it should move. It should move through the die. That is why we have to provide some clearance to flow of the material. And if clearance will be there, then only your punch will get inside the die. So we have to provide clearance. So the second difference between punching and blanking is the clearance. So in the punching, we provide clearance on the die, and in the blanking, we provide clearance on the punch. So, do you know why we do that? Can anyone tell?
In blanking, our main intention to get that in blanking, when the main uses of the blank, the round portion, so it should be of the correct size.
Correct.
That's why the clearance is given on the punch. And when we are doing the punching, the scrap is of no use. That is why the clearance is given on the die side.
Okay, fine. So you have to remember that in punching, your die will be of, in punching, your punch will be of correct size, and in blanking, your die will be of correct size. And this is the formula for the size of punch and the size of die. So your punch, in punching, your punch will be the size of hole, and the die will be punch size plus 2 into clearance. Clearance we will see. Then the in blanking, the die will be of the size of product, and the punch will be the size die size minus 2 into clearance. Now, what is clearance? So this is the formula of clearance. That C is equals to 0.003 32T root tau, where tau is the shear strength and T is the thickness of your sheet metal. Okay. One more in the question, if it is not given, then you have to find it like that. But mostly they will give you clearance in the form of percentage or in the form of allowance. So suppose in the question, if it is given that the clearance is 1%, then you have to take it off 1% of the thickness of your sheet. Same for the allowance. Okay. Now,
is this total clearance or radial?
radial. See, if they are giving radial clearance and they will give you allowance also, so you have to plus both, add both. Okay?
Two times.
Not two times. Suppose in some in there will be one question, then they will give you the radial clearance and they will give you allowance also on the material. So you have to plus both of it and then you have to minus. We'll see.
2C plus 2A, ma'am.
Sorry?
Means it will be 2C plus 2A.
No, no. Uh, allowance will be given on the material. So suppose it will be, suppose a blanking operation. So your punch dimension will be die size minus 2 into clearance minus allowance. Okay. Clearance, both the side we are giving, that's why we are using minus 2. Okay, so now solve this question.
A option, ma'am.
Okay, correct. So first tell me, what is this operation?
Punching. In punching, punch is of correct side. But it looks like blanking from the question.
Yeah, it is blanking actually. Why we are getting confused regarding punching and blanking?
They have given it is to be punched.
Yeah, but see, in most of the
20 dia. So the metal
huh,
disc is of the use.
yes,
For that it should be breaking.
yeah. See, in most of the blanking question, you will get this same language that a metal disc of 20 mm diameter is to be punched. If you feel it is punching, then you'll do it wrong. This is a blanking operation because in this it is shown that your metal disc is important. So that is a blanking operation. And one more thing you can understand that if it was a punching, if it was a punching operation, so punch will be of correct size. So your punch will be of 20 mm only, right? If there is any options here with in which punch is 20 mm,
No.
no, right? So this is clearly not punching. This is blanking. So now if this is blanking, can you solve? Now we have to find the punch dia or punch dimension. Punch dia will be here die size, your hole size minus 2 into clearance. Clearance is what? 3%. We will solve this. What we will get?
Option A.
Option A, 19.88 mm. Any doubt in this? Okay. Now come to punching force or planking force. So this is a simple equation that whatever the shearing area, firstly you have to calculate the shearing area, on what area your shearing action is going to be happen, that area multiplied by your shear strength. That will be your punching force. So this is very important that you should know. This is also when your holes are smaller than the stock thickness. That when your holes, that holes which you are making are smaller, those diameter are smaller than your thickness of the sheet, then you have to use this formula. Otherwise, this formula you will use. So this mostly they is not in your syllabus, but you should know. And this formula you should know always. Tau into area of sharing. Now solve this question.
And basically, punching force is applicable for both blanking and the piercing.
Yes, force will be the same equation.
B option.
B is correct. Okay, let's read this question. A rectangular hole of size. So we are going to make a rectangular hole of size 100 mm cross 50 mm is to be made on a 5 mm thick sheet of steel having ultimate tensile strength and shear strength of 500 MPa and 300 MPa respectively. The hole is made by punching process, neglecting the effect of clearance, the punching force. What is the punching force formula? F is equals to uh, your shear strength multiplied by area of sharing. So what will be the area of sharing here? Your hole is rectangular.
Perimeter into thickness.
Okay, your yeah, correct. Your hole is rectangular. So this wall, this wall, and this wall. These wall will be the shearing action, right? So you have to calculate the area of these walls. This is your sheet. This is rectangular hole which is going to be made. So your shearing action will be on these area. So you have to first calculate this area. So how much it would be? This is 100. This is thickness. You say it is what 5, and then this is as 50. So it will be 2 into 50 into 5, this area 2 times plus this area 2 times, right? Plus 2 into 5 into 100. So this will be your sharing area. This will come as 1500. 1500 and your shear strength. See, they will always give you two strength tensile and you have to choose one. So we know that the most of the metal cutting operations are being done by shearing action. So we have to take the shear strength, which is 300. So it will be 450000. So option is in kilonewton. So this is your Newton. Your 450 kilometer will be correct. So your option B is correct. Any doubt in this?
Mostly we consider shear strength only, not we eliminate the ultimate tensile strength.
Yeah, you have to which will be responsible for the cutting action. See, you're applying shear force. There will be a shear strain. So you have to take the shear strength. That we are overcoming now. We are overcoming the shear strength. That is why your cutting action is happening. So you have to take shear strength always.
Yes, ma'am. And also we need not consider any factor of safety. We can directly take this shear strength.
Yeah, it is not mentioned, so you don't have to consider. That factor of safety and all comes when you're designing the structures or you're designing the tool. Here you want your material to be failed, right? You want to cut it. So factor of safety doesn't matter here because you want this material to be failed. You want to cut it, right? You want it to be failed. So it doesn't matter here. You don't have to think about that.
Yes.
Okay, solve this question also. Yeah, 0.25 is correct. So let let's read this. The ratio of press force required to punch a square hole. There is a square hole of 30 mm, and the thickness is also given 1 mm of aluminum sheet to needed to punch a square hole of 60 mm side, and thickness is given as 2 mm. So what is your force? See, it is the same material, so your shear strength will be same for both the material. Still we will write for less A1 and this will be A2. So for square, it will be L into T, that is 30 into 1. Here it will be 60 into 2. So F1 by F2 will be 30 divided by 60 into 2, it will be 0.25. Okay, any doubt in this? It will be 4 if you are calculating area, that I have already cancelled. Any doubt in this? Hello? Okay. So this is one more equation to calculate the minimum diameter of piercing. So that you should know this equation, that if your what will be the minimum diameter if your piercing pressure is equal to the strength of the punch. So at that, whatever the diameter will be available will be the minimum diameter that you can pierce. Here that sigma c is crushing strength of your punch. Okay. So see, minimum diameter of piercing why we consider, because suppose you want to punch a very small diameter on your sheet, and punching pressure for that diameter will be fixed, right, of the sheet. So what is the strength of that punch? If the strength of the punch is lesser than the piercing pressure that you have applied, then your punch will be crushed. So that is why there is a limit of minimum diameter that can be made by a punch of a particular strength. So this is the equation. Suppose in the question they will give you the crushing strength of your punch and the minimum force that you are applying, and then they will ask you what will be the minimum diameter of piercing that can be done on your sheet metal. So this is the condition that you have to use, that the applied force will be equal to the strength of your punch. Now solve this question. Yes, B is correct. So let's read the question. A hole is to be punched in a 15 thick plate having shear strength of 3 MPa if the allowable crushing stress in the punch is 6 MPa, the diameter of the smallest hole which can be punched. So the condition to get the smallest hole, that the applied force will be equal to the strength of your punch. Applied force will be tau s into pi dt, right? So tau is given as 3 into pi, d we have to find, and thickness is given as 15. Then your crushing stress is given as 6 pi by 4 d square. That is the cross section area of your punch, and d we have to find. So this all will be cancelled out. So d will be 15 into 2, that will be 30 mm. So your option B will correct. Any doubt in this?
Okay, please explain this part about how we find the smallest. Like as a kid, this question is
See, see, for suppose you want to make a very, this is your 10 thickness sheet, okay, and you want to pierce very small holes. That is of suppose 0.5 dia, okay. And now, for to make a 0.5 dia on a 15 thick sheet, what size? Ignore the clearance. What size punch you need? What will be the size of your punch? 0.5. Okay, so you can feel that this is very thin, right? It is very weak. This will be very weak. And suppose the pressure which needs to be the pressure which is required to make a hole to do the shearing action, that is higher than the strength of this blank, because the dimension of this punch is very less now, right? So if the pressure, if the force which is required to make the piercing here is greater than the strength of this punch, then this will sorry the strength of this punch, then this will crush right in between. When you will try to do the piercing operation, then it will be crush, right? It will not be able to make a pierce here, right? So that is why, hence, there comes a condition for minimum diameter that can be made on a sheet. You understood?
yes, but below which the strength of this.
Yeah, below which, suppose after that, this will be crushed. Your punch itself will get crushed, or it will fail first before failing of your sheet. So that is why this condition comes. Maximum you can go uh, up to the dimension of your sheet. So that is why this concept comes.
Yes, but
Okay. Now solve this question. Yeah, 1 is correct. So this is a similar kind of question. A hole of diameter 35 is to be punched in a sheet metal of thickness T and ultimate shear strength 400 MPa using punching force of 44 kilonewton. The maximum value of P is. So the condition is, here also they are asking the maximum value that can go. to make a to get a diameter of 35 mm. So we will use the same equation. So what was the equation? Punching force should be equal to the strength of your punch. So punching force is 44 kilonewton, and your strength will be diameter to 400 into T pi dt. So it will be 44, 3.14, 35, 400 will be your thickness. When you calculate this, it is coming as 1.000 something. So your option A is correct. Sorry, option B is correct. C is correct. Okay. Now solve this question also.
C option.
Yes, option C is correct. Any doubt in this question? Let's read the question. With a punch for which the maximum crushing stress is 4 times of the maximum shearing stress of the plate, would be the diameter of. So we will write the R equation. So it will be pi dt tau s should equal to pi by 4 d square, and instead of sigma c we will write 4 tau. When you will solve this, it will come as d is equals to t. So your option C is correct. Now move on to shear on punch. So sometimes instead of making a this kind of a punch, they provide some shear on your punch. So this length is called as shear. So they give it this shape. So there are some advantages of shear on your punch, that it will reduce the shearing force. The force which is required to do the shearing action will be lower, and it will distribute the cutting action over a period of time, and the maximum force that will be applied will be reduces. So this one more thing that you should know, that this thing is called as shear on punch. What they do, they change the shape of the punch and they provide some shear angle, slanted angle in your punch. So by doing that, your force required will be changed as these formulas. Like now your F will be whatever the F you are getting before with that size, multiplied by P into T divided by S plus P into T for the circular hole. And second formula is for the shear cutting. This is for shearing, this is for shear cutting when it is not circular. And there are two conditions. Firstly, if your force in your question, if it is giving that your force versus displacement curve is trapezoidal, and here your P is the penetration of punch as a fraction, and S whatever the shear that is given on the die, this length will be your S. So this is also kind of important that you should know. If they have provided shear on that, then what will be the formula? Now write this formula, and then try to solve this question.
Please show formula. Actually, the P and S terms.
Which terms? See,
P and S.
F max we know piece penetration in the fraction. See, you're after the penetration up to some thickness, after that your material will start failing. So that penetration is in some fraction they will tell you. So if you read this question, you will understand that is your penetration depth. That would be given in your question. Thickness is the thickness of the sheet, and shear, whatever the height that I have shown here, this height, that will also be given in the mm only. F max is whatever the force that we were calculating, that sigma into as, that is here that force. Now the force will change. That force, how it will change, that is defined by these formulas.
Yes, basically shears that length due to this
Yes, yes,
angle.
yes. Okay. Uh, solve this both the questions. There are two questions. First solve the first one and the second one.
A option, ma'am.
For the first one? Yes, ma'am. Yeah, correct. Solve the second one also.
B option, ma'am.
For second one?
Yes.
Oh yeah, B is correct. Okay, let's read this question. In a shear cutting operation, a sheet of 5 thickness is cut along a length of 200 The cutting blade is 400 long and zero shear is provided on on the edge. The ultimate shear strength of the sheet is 100 MPa and penetration to thickness ratio is 0.2. Neglect friction, assume force versus displacement curve to be rectangular, the work done. So here, sorry, here they're asking to calculate the work done. So formula for the work done will be maximum force multiplied by punch travel. Okay, force into distance. Displacement is your work done. So this is your work done. So firstly we have to find the force, then we have to find the punch travel. How much the punch is traveling. So for that, for force it will be tau into As, right? As is what? This is the cut is along the length. So that you know that it is cutting along the length. So your area of shearing will be 200 multiplied by whatever the thickness is given, 5. And then your tau is given as 100 MPa. So your F max will be what it will be 100 kilonewton, right? Now the punch travel. So it is in the question it is given how much the penetration. So penetration to the thickness ratio is zero point 0.2. So what is the penetration here? Zero point 0.2 multiplied by the thickness. So penetration is 1 point no just 1 mm. So your punch, yes.
Easy. How it is reading 200 into 5 because they have shown 400 on. Right?
See in first question it is mentioned that it is cutting along a length of 200 only. So the length of your maybe your length of your sheet will be up to here only, right? Maybe it is your punch is of bigger size, but your sheet is of only 200 only. You understood? So this is the dimension of your sheet. So what is the area of shear that we have considered of our sheet, right? That is given for the this dimensions are given for the punch. We have to calculate for the shearing area that we go for the sheet. So now that we have calculated the penetration, so that penetration will be your punch travel. So after we have calculated the maximum force, how much our punch will be travel, how what will be the displacement, so we can get the work done. It will be work done will be 100 multiplied by 10 to the power 3 into 1 multiplied by 10 to the power minus 3. This was in mm, this was in kilonewton. So your work done will be 100 joules, right? So your option A is correct. Yeah, yeah. Go from like basic only. So it is given, everything is given in your question. So now next, the second part. Next, move on to second part. Then in the second part, they have provided a shear that is of 20 mm on the blade, assuming force versus displacement curve to be trapezoidal. Whenever, whenever they will give you this uh, shear, they will mention that your force versus displacement curve will be trapezoidal. Then they are asking you to calculate the maximum force. So what was the formula here for shear cutting and trapezoidal mentioned in the question? Your formula is F is equals to F max into PT divided by S, right? Now, now in the question, it is mentioned that the cut we are making is along the length of 200 mm. But here they have given the shear of 20 mm for 400 mm length. So, but you have to cut along this length only. Here only around, suppose if we suppose this is 200 mm, so till this length only your material will cut, right? This will is not of our interest. So we have to get this height. This will be our shear for the 200 mm length. So can you calculate what will be the this what will this length? This is 200. This is 200. This is 20. Then what will be this? You can use similar triangle. Tell me what will be this length? 10. So this will be 10 mm. Now this will be S for us. This will be S for us. So now put all the values and take me the answer. So your F max was 100 kilonewton, right? Into 10 to the power 3, and P was 1.2, 1, sorry, 1. T was 5, S was, what is this? 10 kilometer. Any doubt in this? Any doubt in this? Okay. Okay. The one more thing, spring back. So we have already seen the spring back. Now, tell me, spring back will be more in sheet metal or in bulk forming?
In sheet metal.
Why?
But in my opinion, bulk would be because elastic modulus is the more.
Uh, Suppose we are, okay, I'll give you a condition. We are having one material, suppose aluminium, and we are doing bulk forming for the aluminium and the sheet forming also. Now tell me, in which spring back will be more and why? So we know that spring back will be more in the sheet. Now the material is same. So elastic modulus will be same here also and here also, right?
It depends on moment of I will moment of India.
Spring back. See, why it is more in sheet metal? Your spring back is depend upon the yield strength, right? Suppose your yield strength is very high, so your spring back will be more, right? If your elastic modulus is high, then your spring back will be less, right? So suppose this is your stress strain curve, and this is your yield strength, sigma yield. this is your this is your UTS. So in the bulk form, if you're deforming something, so if your material is having high, it will have high stiffness, right? So to deform that material, you have to, one thing is sure that to deform sheet metal and to deform bulk forming, which will take greater force. Bulk, obviously. So to deform this, you have to go up to here, like below UTS, you have to go up to here. After yield strength, you have to go further to deform the bulk material. But for the sheet material, you up after yield strength only, after you reach yield strength, you'll go little further, you'll be able to deform your sheet metal. So that is why the plastic deformation that is happening in your sheet metal is not much as compared to the elastic deformation. So that is why the elastic recovery will be more in your sheet metal forming than the bulk forming. Okay, so this you should know two, three things about the spring back. What is a spring back, and on what parameters it depends, and why it is more in the sheet metal. Now, solve these two questions. Tell me the answer. First one, ISRO one. Solve and tell me the answer. No, option A is correct. See, don't get confused for just what I said here. Uh, your spring back will depend on your material properties only. So if it is having higher elasticity, then your spring back will be less. Okay, so option A is correct here. Solve this question also. Yeah, this is correct. A is correct. Any doubt in these two questions?
Actually, regarding spring back, you told that elastic recovery is more in sheet metal.
Yes. See. Okay.
Remember?
See. this suppose we have applied pressure up to here in sheet metal and up to here in bulk. So, so see here, whatever the elastic deformation will happen, this will be your recovery, right? This will be your see. I'm trying to tell here. Up to yield strength, whatever the deformation will be happen, will be recovered, right? So to deform the sheet metal, you don't have to apply much load. So your plastic deformation is not as more as your elastic deformation, right? In the sheet metal operation.
Remember elastic recovery.
Yeah. So whatever the elastic deformation is happened after the removal of the load, that much deformation will be recovered, right? That is what we call elastic recovery or spring back. Okay. So you can tell that in the bulk forming, your plastic deformation will be so high as compared to your elastic deformation that we mostly ignore that elastic recovery in your bulk forming. But in your sheet metal, because the thickness is very small, it cannot be ignored. It will be significant. Suppose there is a very thin sheet here and you try to deform. You want this kind of shape for your sheet metal. So it will not take much. And suppose there is a bulk block of certain height, and you want to deform it like you want to deform its height to here. Okay, so one thing we know, this will take less force, and this will take higher force to get deformed, right? But after your yield strength, if you'll apply little force only, you'll be able to deform this, right? But you applied as much as force that will be able to deform it in this shape. But in this also, most of the deformation that is happened that you applied force for taking into consideration for this shape, that is of elastic plus plastic, and in this case your elastic deformation up to here below the yield strength is higher than your plastic deformation. So the spring back, most of the deformation that is happened will be recovered, right, in this condition. But in your bulk deformation, your plastic deformation will be very much because all of the dimension are of above 20-30 mm. So all your full area will be deformed up to some volume. So your plastic deformation is much higher here as compared to here. You're getting my point?
Which means, like, for example, if they're using the same material,
Yes.
so we'll have the same instinct, right? So it's just a fraction which matters.
Yes.
Yes. Ma'am, can you go back to that question?
Which one? This one?
In a 2003 question,
Yes.
option C also correct.
Release the stored energy in the sheet metal. See, spring back what we are considering, that whatever the elastic recovery. So there will be some stored energy after the plastic deformation also, right? See, it is not mentioned what kind of energy. Full area under the curve we considered as strain energy, right? So it is not mentioned. So we are not going to recover energy which is being stored after the plastic deformation, right?
Okay, so it is not specific. That's why we are not going.
That is why. If it is mentioned elastic, then we can consider this also strain energy or something. Okay. Okay. Now solve this question. Yeah, C is correct. Okay, let's read this question. A shear strength of a sheet metal is 300 MPa. The blanking force to produce a blank is of diameter will be pi dt. When you'll calculate, it will be coming as 141 point. So your option C is correct. Any doubt in this? Solve this question.
5.026.
Yeah, 5.02 is correct. So we can solve this question, right? Should I solve and we can move on next question? Five. Okay, yeah, let me write that. Is 5.024 kilonewton. Uh, Now solve this question. This is also similar question.
B option.
Yeah, option B is correct. Again, same only. Pi dt tau is equals to F. You fill all the values. Everything is given, I guess. Then your option B is correct. It will come around 301.44 kilonewtons. Solve this question.
C option.
Hmm. This is the same question only, I guess. We have to calculate the punching force. It will be pi dt tau is equals to F. You fill the values, F will be 5.03 kilonewtons. Solve this question.
B.
Yeah, B is correct. D pi dt tau is equals to F. You fill the values, your answer will be coming as 392.5 kilonewton. Option B. Now solve this question.
A option.
Yeah, option A is correct. Okay, let's read this question. The force requirement in a blanking operation of a low carbon steel is 5 kilonewton. The thickness is T, diameter is D. For the same work material, if the diameter of the blank part is increased to 1.5 T, the thickness is reduced to 0.4 T, the new blanking force. So it will be your F, because this is F2 will be 3. Any doubt in this? Solve this.
A option.
Yeah. Option A is correct. So again, first we have to read first. The 10 mm diameter holes are to be punched in a steel sheet of 3 mm thickness. Shear strength is given. Penetration is 40%. Shear provided on the punch is 2 mm. The blanking force. So firstly, we will calculate F max. That will be pi dt tau pi dt. Tau is what? 400. So F max will be, calculate and tell me.
37.7
37, right?
Yes, ma'am. 37.
0.7 kilonewton. Then your P by T is given as 0.4. 40% of your that 40% is given. So P by T is given as 0.4. So your P will be 0.4 multiplied by 3, that is 1.2. Now what is the formula? The formula is F max into PT divided by S plus PT. Now put all the values in this formula. And sorry, what is F? What is the final answer? 20. You'll get in the range of 22 to 25 kilometers. Your option A will be matching. Okay, any doubt in this? Yes.
Yeah, since it is mentioned circular hole like diameter is mentioned, we have used this. I mean, if it is trapezoid, it will be mentioned.
Trapezoidal was the shape of the force displacement curve. See, if you're not providing any shear, then the force displacement curve will be like this. Mostly we need force displacement curve to calculate the energy which is required. Okay. When you're using shear, or maybe it will be rectangle when you're not using any shear. But when you are providing any shear, it will be trapezoidal form, because initially it will increase your shear force, it will be then constant, and it will be decreasing. So this will be your force trapezoid. Sorry,
I am getting 14.13.
14.
14.
I also got 24 something, but I used yes.
1 4. That, regarding 40% penetration, we should be after when we got 1.2. Again, we should multiply thickness for that because it is already multiplied.
I think we have to multiply, that is in the formula, right? P.
Ma'am, here P was the fraction, in fraction only, that is 0.4.
Yes.
We have to multiply the P.
Yeah, we have to multiply.
Given in mm.
Yes.
And if we don't multiply by T, then how does the unit will match?
Yes, correct. We have to multiply here.
ओपन करके तो 14.13 kilonewton आ रहा है ना.
Is it?
Ma'am, in the formula we have to ignore in the denominator PT because PT is less than the given shear.
Wait, but I have calculated with the same formula and I got the answer. Wait.
मैम अगर PT को नेगलेक्ट करते हैं तभी आ रहा है, नहीं तो नहीं आ रहा.
I am getting 24.2 without neglecting PT. If you neglect the PT, it will come as.
Ma'am, S plus PT is 3.2.
See, PT will be your PT will be 1.2 into 3. That is 3.6, right? So S plus PT will be 5.6, right? Then your F max here you don't directly put in kilonewton. You write 37 point what was covered 37.7.
Ma'am, P is 0.4 and PT is 1.2.
Penetration is provided as 40%. Okay, fine. Okay, I think I have done right only. I will check this question and get back to you on next session. Okay.
Ma'am, usually we have seen both the formulas for circular holes only. It's like one with shear and one without shear, right?
Yes.
It's just the shape which matters, which is due to the shear and due to.
Shape matters actually. I have shown you two formulas. One is for circular hole and one is for shear cutting only. So this one we have used in the previous question. This we are using in the question that we are solving now. So I will check this question again because when I use this formula with the same thing only I got the answer. So I will check this question again. Okay.
Yes, ma'am. The formula is actually both for circular hole, one with shear, one without shear.
No, not like that. First one is when you're doing for circular holes. Second, this formula when you're doing any shear cutting. Like in this, what we are doing, we are not making any holes here, right? In this question. Have you read this question? In a shear cutting operation, we are not making any holes here. A sheet of 5 mm thickness is cut along a length of 200 mm. So there is just a sheet. With the help of punch, we are cutting that sheet. That is why we used this formula. Here we are making a circular hole. You understood?
Yes.
So in this question we use this formula. In the later question that we have doubt on, we have to use this formula. Okay, I'll get back to you for this question. Because when I solved, I got the answer. Now move on to take a screenshot of this question when you solve. We'll discuss this. Now solve this question.
D option.
Yeah, option D is correct. We don't have any doubt in this, right? So, okay, tell me what is this operation? Blanking, right? In the blanking, your die will be made of the whole diameter. Okay, so any option C or D will correct. So you have to get the uh, other dimension, that is punch dimension. When you'll calculate that, we'll calculate the clearance. It is the 6% of your sheet thickness. Then we will calculate the punch dimension.
The answer is C, ma'am, not D. You are getting C, ma'am.
Okay, after solving this, you are getting C. Sorry.
Yes, ma'am, I am getting C.
Solve this. What is it coming?
Ma'am, 49.70. But after 50, the total clearance would be uh, 50 minus 0.30.
Okay. 50 minus. Okay, this is coming as, this part is coming as 0.3.
Total clearance.
It will be 49.70. So your option C is correct, not D.
0.1 second.
Sorry?
Actually, I'm telling that the radial clearance would be 0.1 second. It's point.
Okay, I got it. There is a confusion between total clearance and radial clearance. That also we will.
0.3.
Sorry? Oh, yeah, that is coming 0.3 only.
Total clearance. Radial clearance just is.
Sorry? The radial clearance is given. So if you'll use just the radial clearance, you will get the option D. Otherwise, you will get the option C.
So actually, if they ask just radial clearance, is it just C only? Only once we should consider it.
Yes.
Without the two.
Yes. Okay. Okay, now solve this question.
C option. C.
Yeah. Solve this question.
Once. A option. B. Here.
Yeah, it is coming as option A. Again, work done will be force into displacement. First, we will calculate. Okay, force is given only 2 into 10 power 5. What is the displacement? Coming as 4 into 0.25, right? So W will be 200 joules. Option A is correct.